April 23, 1943, 11:15 hours, Medjez el Bab, Tunisia. Hauptmann Friedrich Weber stood beside a captured American M4 Sherman tank, its olive-drab paint scarred by small arms fire but otherwise intact. The crew had abandoned it during the previous night's engagement when German forces overran a forward American supply position. Weber commanded a reconnaissance unit of the 15th Panzer Division, and his orders were clear. Evaluate enemy equipment, document technical specifications, report findings to division intelligence. The Sherman sat motionless in the morning heat, North African sun already pushing temperatures past 30 degrees Celsius. Within hours, the temperature would climb past 40 degrees, the kind of heat that turned tank interiors into ovens, that caused engines to overheat and seize, that killed careless soldiers through heat exhaustion. Weber had been fighting in North Africa since 1941. He understood desert, warfare's brutal realities. Heat was as dangerous as enemy fire. Weber's crew gathered around the abandoned vehicle with professional curiosity mixed with skepticism. They had heard reports about American tanks from units engaged at Kasserine Pass 2 months earlier. The Americans had performed poorly in their first major engagement against German armor. Poor tactical coordination, inadequate training, confusion under fire. Green troops making mistakes that veteran German tankers exploited ruthlessly. The Sherman had seemed like just another inferior Allied tank design, adequate perhaps for colonial warfare, but unsuited for fighting German Panzers. Weber climbed onto the Sherman's hull and examined the exterior carefully. The tank was smaller than he expected, lower profile than German medium tanks. The armor looked thin, especially compared to the heavy plating on newer German designs. He pulled a measuring tape from his pocket and checked the frontal armor thickness. Approximately 50 millimeters, angled at roughly 56 degrees. Simple geometry and basic ballistics knowledge told him this was inadequate against German anti-tank guns. A Panzer IV's 75mm gun would penetrate this armor easily at combat ranges. The riveted construction seemed primitive. German tanks used welded armor plates for superior strength and protection. Welding created monolithic structures where force distributed across entire plates. Rivets created weak points. A solid hit on riveted armor could send rivets flying inside the crew compartment like shrapnel, killing crew members even without penetrating the armor completely. German engineers had abandoned riveted armor construction years ago. Yet here was an American tank, built in 1942 or 43, based on its condition, still using outdated assembly methods. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The turret mounted a 75mm gun, respectable but not exceptional. German Panzer IVs carried the same caliber weapon. Weber examined the gun barrel carefully. The Sherman's gun had a shorter barrel than the Panzer IV's KWK-40, suggesting lower muzzle velocity and reduced armor penetration capability. He estimated the barrel length at roughly 40 calibers, while German 75mm guns used barrels of 48 calibers or longer. That difference translated directly into reduced performance. The tracks were relatively narrow, which would create higher ground pressure and worse cross-country mobility in soft terrain. German tanks used wider tracks to distribute weight more effectively, allowing better performance in mud, sand, and snow. These narrow American tracks looked like they would sink in soft ground, bogged down in conditions where German panzers could maintain mobility. Everything about the Sherman's external appearance suggested a mediocre design, functional but unremarkable. Weber had expected nothing different. American industry was vast, capable of producing enormous quantities of equipment, but German technical expertise was superior. Everyone in the Wehrmacht knew this. It was stated in training materials, reinforced by propaganda, confirmed by early war victories. German engineering excellence versus Allied numerical superiority. Quality versus quantity. Weber's assessment aligned with prevailing German military opinion in spring 1943. American industrial capacity was acknowledged as vast, but American engineering was dismissed as crude. German officers believed their tanks were technologically superior, better armoured, better armed, built by skilled craftsmen rather than assembly line workers. The Panzer III and Panzer IV had proven themselves in France, in North Africa, on the Eastern Front. German armour doctrine emphasized quality over quantity, precision engineering over mass production. Weber ordered his crew to start the Sherman's engine. They needed to evaluate its mechanical condition, determine if it could be pressed into German service as a captured vehicle. His driver, Obergefreiter Hans Richter, climbed into the driver's position. Richter had been driving Panzers since 1941. He knew German tank controls intimately, understood the temperament of Maybach engines, the characteristics of German transmissions and steering systems. He had started hundreds of Panzer engines, knew the precise procedures required to avoid flooding carburetors, to prevent backfires, to coax cold engines to life without damage. The Sherman's interior was completely different from German tanks. The controls were laid out simply, almost crudely. Large levers, prominent gauges, everything designed for ease of operation rather than technical sophistication. Labels in English marked every control, every switch, every instrument. The kind of labeling that assumed operators might not have extensive training, that emphasized clarity over elegance. Richter found the starter switch, a simple toggle clearly labeled in English. He examined it briefly, understanding its function from context even without reading English. He engaged it. The Wright Continental R975 radial engine turned over immediately, caught, roared to life with a distinctive sound completely unlike the smooth rumble of a Maybach engine. The engine note was rough, mechanical, almost industrial. Not the refined sound German tankers associated with quality engineering. It sounded like a truck engine, like industrial equipment, not like a precision machine built for military service. But it started instantly. No priming required, no careful procedure to prevent flooding the carburetor, no warming period before engaging the clutch. Just flip the switch and the engine ran. Richter sat in the driver's seat for a moment, listening to the engine, feeling the vibrations through the timer hull. German Panzer engines needed warming up gradually. You started them, let them idle, monitored temperatures and oil pressure carefully before engaging the transmission. You treated them like the sophisticated machines they were. This American engine just ran at full idle immediately, no ceremony, no careful attention required. He reported this to Weber through the intercom system. The captain noted it but assumed the Sherman had been recently serviced, still had fresh fuel and oil, had not yet experienced the mechanical stress of sustained operations. Any engine would start easily when properly maintained and recently operated. The real test would come after hours of running in desert heat, after mechanical stress revealed design weaknesses. Richter tested the controls. The transmission shifted smoothly through all 5 forward gears. No grinding, no resistance, no need to double clutch or carefully time the shifts. German Panzer transmissions required skill to operate properly. You had to match engine speed to gear speed, to time clutch engagement precisely, to understand each gearbox's individual characteristics. Experienced drivers developed feel for their specific vehicle, learned its quirks through hundreds of hours behind the controls. The Sherman's transmission felt like it had been designed for inexperienced operators. It shifted easily, almost automatically. The synchromesh gearing made gear changes smooth regardless of technique. The clutch engaged cleanly without requiring precise timing. The whole system felt simple, almost agricultural in its straightforwardness, but it worked effortlessly. The steering levers required minimal effort, far less force than German steering clutches demanded. German tanks used clutch and brake steering systems that required significant physical strength to operate, especially when making sharp turns or maneuvering in difficult terrain. Tank drivers needed to be strong young men specifically because operating the controls was physically demanding. Richter had arm and shoulder muscles developed through thousands of hours wrestling with steering levers. The Sherman's steering felt light, almost easy. He could turn the tank with minimal effort. This seemed wrong somehow. Sophisticated machines should require skill and strength to operate. This simplicity suggested crude engineering, systems designed for the lowest common denominator rather than for excellence. Weber ordered a test drive. Richter would drive the Sherman along the nearby road for several kilometers, while Weber and the rest of the crew followed in their SDKFZ 250 half-track. They would observe the Sherman's performance, note any mechanical problems, evaluate its mobility characteristics. If the tank proved functional, division headquarters might authorize its use as a command vehicle or send it to a testing facility in Germany for detailed evaluation. Captured equipment sometimes proved valuable. The British Matilda tanks captured in France in 1940 had been pressed into German service in North Africa. Soviet T-34 tanks captured on the Eastern Front were sometimes operated by German units when their own vehicles were unavailable. If this Sherman proved mechanically sound, it might serve similar purposes. Richter drove the Sherman out of the abandoned supply position onto the dirt road heading south. The transmission responded smoothly to every gear change. The engine maintained steady power without hesitation or missing. The tracks rolled evenly. The suspension absorbed bumps and ruts without harsh jolting. The whole vehicle moved with a mechanical confidence that surprised the German crew watching from their half-track. The road was rough, typical North African terrain, packed dirt with ruts from previous traffic, scattered rocks, occasional sand patches, conditions that stressed mechanical systems, that revealed suspension weaknesses, that caused poorly maintained vehicles to rattle and shake. The suspension side, Sherman traversed it smoothly. The vertical volute spring suspension absorbed impacts effectively. The wide track base provided stability. The tank moved steadily at 30 kilometers per hour without difficulty. After 3 kilometers, Weber radioed for Richter to halt. They would inspect the engine while it was hot, check for oil leaks, examine the cooling system, look for the typical problems that appeared in tanks after even limited operation. Weber expected to find evidence of mechanical stress, signs that the Sherman's crude design was already showing weakness. Richter shut down the engine and climbed out through the driver's hatch. Weber and 2 mechanics approached the Sherman and opened the large engine access doors on the rear hull plate. The Wright Continental engine sat in its compartment, still ticking as hot metal cooled. The mechanics examined it carefully with professional eyes trained to spot problems in German Panzers. There were no oil leaks. The valve covers were dry. The gaskets showed no seepage. German Panzer engines always developed small oil leaks. Always. It was simply the nature of high-performance engines operating under stress. Mechanics expected to find oil seepage around valve covers, around gasket surfaces, around seal points. They carried rags specifically to wipe up oil, to keep engine compartments clean enough that new leaks would be immediately visible. The Sherman's engine compartment was dry, not just relatively clean, but actually dry. No oil residue, no seepage, no evidence of leaking gaskets anywhere. The fuel lines were intact, with no evidence of weeping or cracking. The cooling system hoses were secure, no drips of coolant visible anywhere. The engine compartment was remarkably clean for a tank that had just been driven several kilometers in North African dust. Weber's senior mechanic, Unteroffizier Kurt Schneider, had maintained Panzer IIIs and Panzer IVs since 1940. He knew intimately what German tank engines looked like after operation. There were always small oil leaks around valve covers, always some seepage from gaskets that needed tightening, always evidence of mechanical stress, small problems that required attention before they became major failures. Mechanics spent hours every day managing these issues, keeping engines running through constant attention and adjustment. The Sherman's engine showed none of this. Schneider checked the oil level using the dipstick. The oil was clean, at proper level, showed no contamination or metallic particles. He examined the air filter, expecting to find it clogged with North African dust. Desert dust was incredibly fine, penetrated everything, clogged air filters rapidly. Panzer air filters required cleaning every few days to maintain engine performance. The Sherman's air filter was clean, had been designed with large surface area and easy access for field maintenance. The oil bath air filter design was simple, effective, could be serviced quickly by any mechanic. Everything about the engine installation was engineered for simplicity and reliability rather than sophisticated performance. Schneider reported his findings to Weber. The captain was puzzled. This contradicted German assumptions about American engineering quality. Perhaps the Sherman had been exceptionally well maintained by its crew before abandonment. Perhaps American units in this sector had better mechanics than German intelligence estimated. Perhaps this specific vehicle was an exception, better built than typical American production standards. Weber decided to continue testing. They drove the Sherman for another hour, covering approximately 20 kilometers of mixed terrain, paved roads, dirt tracks, sandy sections, rocky areas, the kind of varied conditions that would stress any tank's mechanical systems, that would reveal weaknesses in design or construction, that would demonstrate whether this vehicle's apparent reliability was real or merely temporary. The transmission continued shifting smoothly through every gear. The clutch operated effortlessly. The steering remained light and responsive. The engine maintained consistent power output without hesitation, without the slight roughness that German engines developed after extended operation. The cooling system kept operating temperatures stable, even as the afternoon heat intensified, even as ambient temperature climbed past 40 degrees Celsius. German Panzers operating in this heat would have been approaching critical temperatures. Drivers would be monitoring temperature gauges constantly, ready to halt if readings climbed into danger zones. Mechanics would be preparing to add coolant, to check for leaks, to manage the constant battle against overheating that defined desert tank operations. The Sherman's temperature gauge showed normal operating range, not even approaching concerning levels. The engine ran cool despite conditions that would have stressed German cooling systems severely. This made no sense to Weber. How could a crude American design handle desert heat better than sophisticated German engineering? Weber ordered a return to the original position. He wanted to conduct a more thorough examination, document specific technical details for his intelligence report. The Sherman was performing far better than expected, and division headquarters needed accurate information about American tank capabilities. If American tanks were more reliable than intelligence assessments suggested, that changed tactical calculations, influenced operational planning. Back at the abandoned supply position, Weber's crew spent the next 3 hours examining every accessible system on the Sherman. They measured armor thickness at multiple points, recording precise specifications. They inspected the track design and measured track pitch, noting how it compared to German track systems. They examined the suspension system, noting the vertical volute spring suspension with relatively simple construction compared to German torsion bar systems. German torsion bar suspension was sophisticated, used twisted steel bars to provide spring action, allowed for low hull profile and good internal volume. It was an advanced system that represented excellent engineering. The Sherman's suspension looked primitive by comparison, using simple coil springs in vertical units. Yet it functioned effectively, provided adequate crew comfort, maintained stability during movement. They climbed inside the turret and evaluated the gun controls, the optical sights, the ammunition storage. The interior was spacious compared to German tanks, with good crew positions and adequate visibility. German tank design emphasized compact size to reduce target profile, but this created cramped crew compartments. The Sherman's larger interior gave crew members room to work, reduced fatigue during extended operations. The gun stabilization system, a gyroscopic mechanism designed to keep the gun steady while moving, was something German tanks lacked entirely. American tankers could fire accurately while driving, a significant tactical advantage in mobile warfare. German tankers had to halt before firing to achieve accuracy. The Americans had engineered a solution to this problem, accepting the additional mechanical complexity because the tactical advantage justified it. The radio equipment was comprehensive. Every Sherman came equipped with a radio, allowing all tanks in a unit to communicate directly. German practice was to install radios only in command tanks, with other vehicles relying on visual signals or couriers. This saved cost and complexity, but reduced tactical coordination. American units could coordinate in real time because every tank commander could communicate with every other tank commander. The radio itself was simple to operate, clear controls, prominent frequency selector, straightforward procedures. German radios were sophisticated, but required trained operators. These American radios looked like they could be operated by anyone with minimal training. Once again, American design emphasized ease of use over technical sophistication. As the sun began setting, Weber compiled his observations into a preliminary report. The Sherman was not the crude, inferior vehicle German intelligence assessments had suggested. It was a competent design, optimized for different priorities than German tanks. Less emphasis on thick armor and high-velocity guns, more emphasis on reliability, ease of maintenance, mass production, and crew effectiveness. But Weber's most significant observation would come the following day, when extended operations revealed the Sherman's most remarkable characteristic, a quality that fundamentally challenged German assumptions about tank design philosophy, about what made weapons effective in sustained combat. April 24, 1943, 0600 hours. Weber received orders to move his reconnaissance unit 15 kilometers west to observe American positions near Taborba. The German position in Tunisia was deteriorating. Allied forces were tightening their grip, pushing German and Italian forces into an increasingly small pocket around Tunis and Bizerte. Reconnaissance was critical to identify weaknesses in Allied lines, to find positions where German counterattacks might break through, to gather intelligence that might somehow change the inevitable outcome. Weber decided to bring the captured Sherman along, both for evaluation purposes and because his unit's own vehicles were experiencing chronic mechanical problems. 2 of his 3 Panzer IIIs were currently non-operational, waiting for spare parts that might not arrive for days or weeks. One had a broken final drive. The other had transmission problems that required components that existed nowhere in Tunisia. Both tanks sat immobile, combat ineffective, while mechanics waited helplessly for parts that might never come. German logistics in Tunisia were collapsing. Supply convoys from Italy were being decimated by Allied air power and naval forces. Fuel shortages were constant. Ammunition was rationed carefully. Spare parts were nearly impossible to obtain. Every panzer required extensive maintenance after each operation, with mechanics working through nights to keep vehicles running. The Afrika Korps was being slowly strangled by supply problems, unable to maintain the mechanical readiness necessary for sustained operations. Richter drove the Sherman while Weber followed in his half-track with the rest of the unit. The morning was already hot, temperature climbing toward 40 degrees Celsius. This was the kind of heat that destroyed engines, caused cooling systems to fail, turned tank interiors into ovens. German tankers knew to watch engine temperatures carefully, to stop frequently, and let engines cool before they overheated and seized. Overheated engines were a constant threat in North Africa. The warning signs were familiar to every German driver. Temperature gauges climbing into red zones, slight roughness in engine sound as cylinder heads expanded from heat, loss of power as timing changed from thermal expansion, sweet smell of boiling coolant. Any of these signs required immediate action, halting before catastrophic damage occurred. After 1 hour of driving, Weber expected the Sherman would need to halt for cooling. German panzers operating in North African heat required frequent stops. Engines ran hot, coolant temperatures climbed dangerously high, oil began breaking down from excessive heat. Careful monitoring and conservative operation were necessary to prevent catastrophic engine failure. Experienced drivers learned to nurse their engines through desert conditions to avoid pushing them beyond safe limits. But Richter did not request a halt. The Sherman continued running without any indication of overheating. Weber radioed to ask about engine temperatures. Richter reported that the temperature gauge showed normal operating range, well below any danger level. The engine was running cool despite the ambient heat and sustained operation. He sounded almost puzzled. German engines would be approaching concerning temperatures by now. After 2 hours, Weber expected mechanical problems to appear. German tank engines required careful attention to cooling, to oil pressure, to dozens of parameters that could indicate developing problems. Experienced German drivers learned to listen to engine sounds, to feel subtle changes in performance that warned of impending failure. The slight roughness that indicated a cylinder beginning to misfire, the small vibration that suggested a bearing wearing unevenly, the minor hesitation that warned of fuel delivery problems. Preventive stops were necessary to check systems, to add oil that had been consumed or leaked, to verify that everything was functioning correctly. Better to stop and check than to continue, until something failed catastrophically. Better to lose time on inspection than to lose days or weeks waiting for repairs or replacement parts. The Sherman simply kept running. No warning signs, no indication of stress, no need to stop for mechanical inspection. The engine maintained consistent power output, the same steady sound it had made when first started. The temperature remained stable in normal operating range. The transmission shifted smoothly, without grinding or hesitation. After 3 hours of continuous operation in North African heat, the Sherman showed no signs of mechanical fatigue. Weber was beginning to understand something profound, something that challenged fundamental assumptions about tank design, about engineering philosophy, about what made a weapon system effective in actual combat rather than on paper. The Sherman was not designed to be the most powerful tank, or the most heavily armored tank, or the tank with the most impressive technical specifications. It was designed to run continuously, reliably, without constant mechanical attention, to operate in extreme conditions without failing, to be maintained by average mechanics with basic tools and common parts, to keep fighting day after day without requiring the intensive maintenance that German Panzers demanded, to remain combat effective not through superior individual performance, but through sustained operational availability. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Wright Continental R975 engine was not a sophisticated design by German standards. It was a radial aircraft engine, originally designed for civilian planes in the 1930s, adapted for tank use through relatively simple modifications. 9 cylinders arranged in a circle, air-cooled, simple construction. The kind of engine that aviation mechanics worldwide understood, that could be repaired with common tools, that used standard parts available throughout American supply chains. German tank engines were purpose-built, liquid-cooled designs, sophisticated and powerful, but temperamental. The Maybach engines in Panzer IIIs and Panzer IVs were magnificent examples of precision engineering, designed specifically for armored vehicle use, optimized for power output and efficiency. They represented years of specialized development by expert engineers, but they required precise maintenance, specific tools, specialized knowledge. When problems developed, repairs needed factory-level expertise and parts that existed nowhere except German supply depots. The Sherman's cooling system was overbuilt deliberately. Massive radiators, redundant cooling capacity, designed to handle extreme conditions with substantial margin for error. American engineers had assumed tanks would operate in deserts, in jungles, in Arctic conditions, everywhere across the globe. They designed cooling systems that could not fail even when stressed beyond normal limits, that provided so much capacity that even partially degraded systems would still function adequately. German cooling systems were precisely calculated, engineered to minimum necessary specifications to save weight and complexity. They worked adequately in European climates, in the conditions German engineers anticipated, but struggled in North African heat that exceeded design parameters. German tankers learned to operate carefully, to avoid pushing engines too hard, to stop frequently and manage temperatures manually through experience and judgment. By noon, the Sherman had been running continuously for 6 hours. Weber ordered a halt not because the Sherman needed it, but because his half-track and the crew needed rest and food. The men were exhausted from heat and tension. They needed water, needed to eat, needed to rest in whatever shade they could find before continuing operations. The Sherman could apparently have continued indefinitely. When they stopped and examined the Sherman's engine again, Schneider found the same result as the previous day. No leaks, no mechanical stress visible, oil clean, coolant level stable, everything functioning as if the engine had just been started rather than run for hours in extreme heat. He ran his hand along the valve covers, feeling for oil seepage. Nothing. He checked every visible gasket, every seal, every junction point where leaks typically developed. Schneider spoke quietly to Weber, his voice containing a note of professional bewilderment. Herr Hauptmann, this engine does not behave like any Panzer engine I have maintained. German engines require attention constantly. We check oil levels every few hours because consumption is significant. We monitor temperatures obsessively because overheating is always possible. We listen for any change in sound that indicates developing problems because early detection prevents catastrophic failures. He paused, choosing words carefully. This American engine just runs. It does not require monitoring beyond normal instrument checks. It does not need constant adjustment. It does not demand the careful attention we give German engines. It simply works, consistently, without drama or difficulty. I do not understand how crude engineering produces such reliability. Weber understood the implications immediately. The Sherman's reliability was not an accident or the result of exceptional maintenance by its previous crew. It was inherent in the design. American engineers had created a tank optimized for sustained operations with minimal maintenance. They had sacrificed some performance characteristics that German engineers prioritized, accepting slightly less power, slightly less speed, in exchange for mechanical systems that would not fail. They had designed for the reality of combat logistics, for the reality of average crew capabilities, for the reality that maintenance resources would be limited, and mechanical stress would be severe. They had accepted that in actual combat, operational availability mattered more than peak performance. A tank that ran consistently was more valuable than a tank that performed brilliantly but broke down frequently. That afternoon, Weber composed a detailed intelligence report for division headquarters. He described the Sherman specifications accurately, including all the technical characteristics his crew had measured and documented: armor thickness, gun specifications, engine power, transmission ratios, all the data that intelligence staff would expect. But he focused his analysis on reliability rather than technical characteristics. He noted that the Sherman's engine operated for extended periods without overheating, without requiring stops for cooling or inspection, without showing signs of mechanical stress even in extreme desert heat. He emphasized that American tanks appeared designed for continuous operations by crews with average, mechanical knowledge, rather than requiring the constant expert attention German Panzers demanded. He suggested that American tank units might achieve higher operational readiness rates, with more tanks available for combat at any given time, specifically because their tanks did not break down as frequently. He proposed that in sustained operations, reliability might prove more important than technical superiority. A force of adequate tanks that remained operational might be more combat effective than a force of superior tanks that spent significant time under maintenance. Weber's report reached intelligence staff at Army Group Africa headquarters in Tunis. The intelligence officers read it with interest, but skepticism. Their existing assessments, based on Kasserine Pass and earlier engagements, portrayed American tanks as inferior to German designs. Technical data supported this conclusion comprehensively. Sherman armor was thinner than Panzer IV armor by substantial margins. Sherman guns had lower muzzle velocity, reduced penetration capability. On paper, comparing specifications directly, German tanks were clearly superior, but Weber's report raised uncomfortable questions about whether paper specifications captured the full reality of combat effectiveness. A technically superior tank that broke down constantly was less valuable in actual operations than a technically adequate tank that ran reliably. A powerful engine that required intensive maintenance reduced a unit's effective combat strength more than a simpler engine with lower peak performance. The intelligence staff filed Weber's report with other field observations, noted its contents in summary documents, but did not significantly modify their overall assessment of American armor capabilities. German military culture valued technical excellence, precision engineering, superior specifications. The idea that simplicity and reliability might be more important than sophistication contradicted deeply held beliefs about what made weapons effective. It challenged assumptions that were central to German military identity. Meanwhile, Weber continued operating the captured Sherman for another week, using it for reconnaissance missions and observing American positions around the shrinking Axis perimeter. The tank performed consistently, never requiring significant maintenance, never developing the chronic problems that plagued German vehicles operating in the same conditions. His own Panzer IIIs, when they were operational, needed constant attention. Transmissions required adjustment after every operation. Final drives developed problems that could only be addressed with specialized tools and expertise. Engines leaked oil continuously and needed frequent top-ups to maintain adequate lubrication. Cooling systems required careful monitoring to prevent overheating. Every mission meant hours of maintenance work afterward. The Sherman needed nothing. Richter drove it daily, sometimes for 8 or 10 hours consecutively, as reconnaissance missions extended through entire days. The engine temperature never exceeded normal operating range, regardless of conditions. The oil consumption was minimal, requiring only routine checks rather than constant additions. The transmission continued, shifting smoothly, without any adjustment to clutches or synchronizers. The tracks stayed properly tensioned without requiring the frequent attention German tracks demanded. On May 2, 1943, American forces launched Operation Vulcan, the final offensive to eliminate Axis forces in Tunisia. Allied armies attacked from multiple directions, overwhelming German defensive positions through superior numbers, firepower, and air support. Weber's unit was forced to abandon the Sherman when fuel shortages made it impossible to continue operations. German supply had collapsed completely. No fuel convoys reached frontline units. Vehicles simply ran out of gasoline and had to be abandoned. The Sherman was still mechanically sound when German forces left it behind, fully functional but immobile for lack of fuel. It had operated continuously for 9 days under German use, required no repairs, needed no spare parts, functioned exactly as it had when first captured. Richter, who had driven it throughout this period, reported to Weber that it was the most reliable armoured vehicle he had ever operated. More reliable than German equipment, more reliable than captured British or French vehicles. It simply worked without drama or difficulty. Weber himself was captured on May 7th, when German resistance in Tunisia collapsed completely. The Afrika Korps surrendered, along with Italian forces, ending Axis presence in North Africa. During interrogation by American intelligence officers, Weber described his experience operating the captured Sherman. The interrogators were surprised by his assessment. They expected German officers to dismiss American equipment as inferior, to maintain assertions of German technical superiority even in defeat. Instead, Weber spoke with professional respect about the Sherman's reliability. He explained that German tanks were magnificent machines when properly maintained, capable of impressive performance, superior to Allied tanks in direct technical comparison. But they required maintenance resources that were no longer available in Tunisia, that would be increasingly scarce as the war continued, that simply could not be provided in actual combat conditions. American tanks were designed for the reality of supply limitations, mechanical stress, and average crew capabilities. That made them more effective weapons in actual combat conditions, regardless of their technical specifications. Weber suggested that American engineers understood modern warfare better than German engineers did. They understood that wars were won by logistics and industrial capacity, not by technical sophistication alone. The American interrogation officers documented Weber's statements carefully, but did not initially recognize their full significance. The United States Army was already committed to Sherman production, with thousands rolling off assembly lines monthly. Whether German officers admired Sherman reliability or not seemed irrelevant to American planning. The Americans would continue building Shermans because they could produce them in vast numbers, supply them globally, and keep them operating under any conditions. But Weber's observations, along with similar reports from other German officers who had encountered or captured American equipment, revealed a fundamental difference in engineering philosophy that would determine the war's outcome more certainly than any individual battle. German engineering pursued technical excellence, creating weapons that were sophisticated, powerful, and impressive in technical documentation and propaganda films. American engineering pursued operational reliability, creating weapons that were adequate technically but superior in sustained use. This contrast was not unique to tanks. It appeared throughout military equipment on both sides. German aircraft engines were powerful and sophisticated, but required frequent maintenance and skilled mechanics with specialized training. American aircraft engines were simpler, used lower compression ratios and more conservative designs, but ran reliably with minimal maintenance. German small arms were precisely manufactured with tight tolerances that ensured accuracy and smooth operation. American small arms used looser tolerances that sacrificed some accuracy and refinement, but functioned reliably in mud, sand, water, and extreme conditions. German military industry had developed in a culture that valued craftsmanship, precision, and technical sophistication. Master craftsmen built weapons to exacting standards, took pride in creating machines that represented the pinnacle of engineering achievement. This approach produced excellent results when resources were abundant, when skilled workers were available, when time permitted proper construction and testing. American military industry developed in a culture that valued mass production, interchangeable parts, and design simplification. Factory workers with minimal training could assemble weapons from standardized components using documented procedures. Any mechanic could repair equipment using common tools and readily available parts from standardized supply chains. This approach prioritized getting adequate weapons to troops quickly, rather than creating technically perfect weapons slowly. In 1943, with Germany already facing resource shortages and manpower constraints that would only worsen, the American approach was proving more effective strategically. German factories produced fewer tanks of higher individual quality, but could not produce enough to replace losses. American factories produced many more tanks, adequate quality, replacing losses easily and building stockpiles. German tank units struggled to maintain operational readiness because repairs required scarce resources and specialized expertise. American tank units maintained high readiness because repairs were straightforward and parts were abundant. The Sherman tank that Weber captured and operated for a week in Tunisia exemplified this American approach comprehensively. Its Wright Continental engine was not a masterpiece of engineering sophistication. It was a proven, reliable design adapted from civilian use, manufactured in quantities that ensured spare parts availability throughout global supply chains, simple enough that any trained mechanic could maintain it with basic tools. The transmission was not a complex 7-speed gearbox like German tanks used. It was a straightforward 5-speed unit that sacrificed some theoretical performance for durability and ease of repair. The armor was not elaborately angled or dramatically thick. It was adequate for protection against most threats, arranged simply to facilitate manufacturing, welded, or cast in forms that assembly line workers could produce consistently without specialized skills. The gun was not the highest velocity weapon available. It was effective against most targets, used ammunition that was standardized and widely available, mounted in a stabilized turret that allowed firing while moving. Every design decision reflected American priorities: reliability over sophistication, maintainability over peak performance, production efficiency over technical elegance. These priorities made the Sherman an effective weapon system, despite its technical limitations compared to German designs. In sustained operations, Sherman units maintained higher percentages of operational tanks than German Panzer units achieved with technically superior vehicles. After the war, captured German documents and interrogation reports revealed that German military intelligence had gradually recognized American equipment's reliability advantage. Reports from Tunisia, from Sicily, from Italy, from Normandy all noted that American tanks rarely broke down, that American supply systems kept equipment operational, that American maintenance procedures were simple and effective. But this recognition came too late to influence German production decisions. Germany's industrial capacity was already committed to existing designs, to production methods that emphasized quality over quantity, to weapons that required intensive maintenance. Changing these systems would have required fundamental reorganization of German industry, retraining of workers, redesign of equipment from basic principles. In a war economy already strained to its limits, such changes were impossible. Germany would continue building sophisticated tanks that broke down frequently, because that was what German industry knew how to build. The United States, conversely, had built its war production around principles of mass manufacturing from the beginning. Henry Ford's assembly line concepts, applied to military equipment, created production capabilities Germany could not match. American factories produced approximately 50,000 Sherman tanks during the war. German factories produced approximately 25,000 Panzer IVs, their most numerous medium tank design, plus roughly 6,000 Panthers and fewer than 2,000 Tigers. The Panzer IV was arguably a better tank technically in many respects, but Germany built half as many. More significantly, American Shermans maintained higher operational readiness rates throughout their service. A typical American armored division could expect 80 to 90% of its tanks to be mechanically operational on any given day. German Panzer divisions often struggled to keep 50 to 60% operational, with the remainder awaiting repairs, spare parts, or comprehensive maintenance. Superior numbers combined with superior reliability gave American armor overwhelming advantage in sustained operations. Weber's week operating a captured Sherman in Tunisia provided him a glimpse of this reality before most German officers recognized it. He saw firsthand that American engineering philosophy, which German engineers often dismissed as crude or unsophisticated, produced weapons better suited to industrial warfare's demands. Technical excellence mattered less than operational sustainability. Individual superiority mattered less than collective reliability. Impressive specifications mattered less than consistent availability. When Weber was repatriated to Germany in 1947 after spending 4 years in Allied prisoner of war camps, he returned to a country destroyed by the war Germany had started and lost catastrophically. German cities lay in ruins from Allied bombing. German industry was dismantled by occupation authorities. German military power was eliminated completely. The Wehrmacht dissolved. Germany divided and occupied. In conversations with former comrades, Weber sometimes spoke about his experience with the captured Sherman in Tunisia. Some listeners dismissed his observations. They preferred to believe German defeat resulted from numbers alone, from being overwhelmed by enemies on all sides, from betrayal or mistakes by leadership. They wanted to believe that German technical superiority was real, but simply overwhelmed by Allied material advantages. This belief allowed them to maintain pride in German engineering, in German military tradition, in the idea that they had lost through circumstances rather than through fundamental errors. Others understood what Weber had recognized in 1943, that German engineering's pursuit of technical perfection had created weapons that were impressive individually but unsustainable systemically. That American engineering's acceptance of technical adequacy had created weapons that were unimpressive individually but devastating systemically. That modern industrial warfare rewarded reliability and production capacity more than sophistication and craftsmanship. The Sherman tank that Weber captured in Tunisia was eventually recovered by American forces during Operation Vulcan's final stages. It was refueled, driven to a maintenance depot, inspected briefly, declared serviceable, and sent back to a frontline unit. No significant repairs were required. The tank had run continuously for weeks under German operation, then sat abandoned for days, and resumed service immediately upon recovery. This was routine for Shermans throughout the war. German military records from Tunisia documented hundreds of Panzers abandoned, not because of combat damage, but because of mechanical failure or lack of fuel. Transmissions broke, engines seized, final drives failed, steering systems malfunctioned. These were sophisticated machines that could not sustain operations without the intensive maintenance, and spare parts that German logistics could no longer provide. The contrast Weber observed between German and American tank design philosophy reflected broader contrasts between German and American industrial civilizations. Germany had industrialized relatively late in the 19th century, retaining cultural values of craftsmanship and technical mastery from its artisan traditions. German education emphasized specialized expertise, deep knowledge in narrow fields, mastery through years of apprenticeship and study. German society valued precision, excellence, technical sophistication. America had industrialized rapidly across the 19th century, developing cultural values of practical effectiveness and scalable production. American education emphasized broad applicability, learning enough to be useful quickly, competence through standardized training rather than long apprenticeship. American society valued pragmatism, efficiency, results over refinement. These cultural differences shaped how each nation approached military engineering, with results that became apparent when sustained industrial warfare tested not just weapons, but entire production and support systems. The Sherman's reliability advantage was not accidental or incidental to its design. It was the central design goal from the beginning. American engineers had studied German and Soviet tanks, understood their performance characteristics and design philosophies, and deliberately chose different priorities. They accepted that Sherman armor would not match German heavy tanks. They accepted that Sherman guns would not penetrate the thickest German armor frontally at long ranges. They designed instead for sustained operational availability, betting that reliable presence mattered more than technical superiority in any single encounter. That bet proved correct comprehensively. By mid-1944 in Normandy, American armored divisions were maintaining operational readiness rates above 85%, while German Panzer divisions struggled to maintain 50%. Sherman tanks fought in every campaign from North Africa through Germany. They operated in deserts at 50 degrees Celsius and in winter at -30 degrees Celsius. They crossed mountains, forded rivers, navigated destroyed cities. They kept running regardless of conditions. German tanks that were technically superior, the Panther and Tiger models introduced in 1943 and 1944, achieved impressive combat records when operational. When Panthers or Tigers engaged Shermans under favorable conditions, German tanks usually won through superior armor and firepower, but they were chronically non-operational. Panthers broke down constantly from transmission failures, final drive problems, engine fires. Tigers required so much maintenance that German units could rarely field more than half their authorized strength simultaneously. Technical superiority became irrelevant when the superior tanks were sitting broken in maintenance areas rather than fighting. Weber's experience capturing and operating a Sherman in Tunisia in April 1943 provided an early indication of this reality. His intelligence report, filed away and largely ignored at the time, described precisely the reliability advantage that would help defeat Germany. The Sherman that never overheated, never broke down, never required the constant attention German tanks demanded, represented American industrial power more accurately than production statistics or technical specifications could convey. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.